post this lecture online, or our session online. All right, so again, welcome. And at the end of project 1, we get to start off project 2. Every time a door closes, another one opens, right? So project 2 introduction, let's just go ahead and quickly go over this. This has been up for a couple of days, and so some of you might have noticed it if you've been on Canvas and have no life like I don't. So project 2 introduction. Project 2 is called Performative Grid Shell, which you would think would be up here, but for some reason isn't. I need to change that, I suppose. But in project 2, we're going to generate and build a performative grid shell system in order to better understand how to leverage parametric design, geometry, performance, and digital fabrication, right? So that's a big, long sentence, but basically we're going to build off of what we've done before, where we started to learn about parametric design and geometry, thinking about points, lines, and curves. Now we're going to expand our geometric library. We're going to start talking about surface. At the same time, we're going to be dealing with, how do we allow the shape of things, the geometries that we generate, right, to be informed by some sort of performative constraints and goals, right? When I mean performance, I mean not like a theatrical performance. I mean like, I'm talking about how something works, right? In other words, oftentimes when you read about, let's say, a particular new model of car, right, it talks about the performance of the engine, right? A high performance vehicle. Right? And so what we're talking about is how something works in relationship to how it needs to work, right? So in other words, what we'll be dealing with is performance as it relates to how something performs in regards to how it shades, right? How it blocks or allows sun through the sort of grid shell system. That was a pretty inarticulate way of putting it, but nevertheless, when I'm talking about performance or performative architecture, that's what I mean. In other words, there's some sort of goals for how this thing should work, and there's ways to measure how well it works, and then we can sort of measure performance, and then we can start to use those performative, even use those performance standards as generative tools for our designing, right? And then also, last but not least, thinking about fabrication and production, right? So it's not like we can just model anything, but it's really kind of hard to make certain things physical, right? And so beginning to sort of understand how production constraints and logics can also begin to inform what we design, right? So understanding that every line, curve, or surface that we draw or model has profound implications on budgets and those other things based on how we make it, right? And what kind of materials we can use. So the basics of parametric modeling, focusing on geometric and parametric properties of surfaces and data trees. In other words, we'll start to look more and more about how the information is stored and organized. There's these things called data trees. We talked about those in project 1, but in this case, we'll actually have to look at them much more carefully. Defining and using performance criteria as a means to test and then generate design options, right? So again, we're talking about these sort of feedback loops, right? Someone just keeps emailing me like in the middle of class. It's really annoying. Anyway, so, but anyway, this idea of a feedback loop where it's not that we can just design anything again, but we can design things that are smarter, better, faster, cheaper, or perform better when it comes to energy and daylight systems, things like that. And then also generating a digitally fabricated model and diagrams showing the rationalization of a doubly curved surface into planar components, right? So in other words, we're going to be taking something that's thick and three-dimensional and doubly curved and breaking it up into a set of components and pieces and parts, right? Just like we would with any piece of architecture. And then think about how to make them. In this case, we'll be using laser manufacturing. And so we'll be looking at how to make three-dimensional components from two-dimensional flat stock, right? So we'll also be looking at the sort of ways that we can, again, create drawings and diagrams, right? In order to communicate to, let's say, fabricators and laborers for how to put these things together. Of course, those will be assembly instructions for you, because you'll be not only laser cutting all these pieces, but then have to sort of really carefully put them all together and construct them like any other model. So the objectives, and this is the real meat here, to integrate performance criteria into your design process in order to generate data and then your design geometry. We'll also be integrating sort of production, fabrication, manufacturing criteria into these models and your design process, right? The idea is that not only will you be producing one model, you'll be producing two models. So you'll produce the first prototype and you'll sort of discover a lot of assumptions that you've made might be a little off. You need to dial in some of those parameters in order to get those tolerances just right. So then the second or final time you make this prototype, things sort of fit together really nicely, right? So again, talking about this sort of idea of iterative prototyping as part of the sort of iterative design process that you guys undertake, right? To leverage underlying geometries, in other words, the sort of surface anatomy, which I'll talk about today and we'll look at primarily this week, in computational data structures, list arrays, and data trees to create a parametric model that's complex and multivalent, right? In other words, we start to build a lot of dependencies, make a really smart parametric model. The idea is that not only can you take a shape and then break it down into pieces, but as you start to think about how they perform, and we'll actually start to cast sun from particular directions through this, you can begin to tweak those parameters, right? Adjust those slide bars, adjust the variables in order to make something that performs better and something that actually, let's say, fits together better when you start to model it and then fabricate it and then assemble it, right? So these three things really start to come together in this project, right? This idea that we need to be able to adjust parameters as we go, right? As we start to gather more information, whether it's the information of material information or whether it's geometric information when it comes to daylighting, right? Demonstrate abilities to generate and format explanatory design and fabrication representational drawings. Okay. Wow, I don't know why I say things so weirdly, but in other words, we're looking at sort of fabrication, shop drawings, these sort of drawings that rely less maybe on the experiential like we did in the first project, where we're just dealing with, let's make a really pretty perspective and put people in it and sort of sell this as a really interesting spatial proposition. Now we're going to be focusing on a representation as a means to sort of show how we take something three-dimensional, turn it into a bunch of components and how those components go together, right? So we'll start to look at things almost like IKEA assembly instructions or exploded axons, but in a way to sort of talk about how things go together, okay? If you think about those, exploded axons, I always think about, some of those, if you ever bought like, those car models or airplane models when you were smaller, younger, and put those together, oftentimes those are all about taking a bunch of pieces, organizing them, labeling them, and then showing how they go together into some sort of larger assembly, right? And that's what we'll be focusing on. So we'll be graphically communicating design intentions, constraints, and the results as we prototype these things. Demonstrate abilities to compose a balanced graphic composition. Again, just getting practice at that. Using Illustrator, maybe some InDesign this time around. I don't want to keep throwing too many new things at you, but I think maybe we can look at InDesign this time for composing our boards and going back and forth between Illustrator and InDesign. That could be pretty useful. And then to demonstrate ability to design and make models, right? So again, this idea that there's a sort of prototyping, it's an iterative process. Oftentimes we'll make something just to figure out how not to make it. Like we just make lots of mistakes, right? The mantra here is fail early, fail often, because what you learn through trial and error sometimes with prototyping is you start to understand when you push on materials, sometimes they push back. And so you start to understand and gain a sort of tacit understanding of what you can and can't do with certain materials and certain tools, right? And what I would argue is that over time, right, with practice, you start to develop this sort of idea of craft, right? This sort of idea of techne, right? That's the root Greek word for the second part of architecture, right? Architect. Comes from techne, meaning the sort of how to make things and how to put things together, right? This idea of craft, starting to understand that process, be able to think steps ahead and apply a material logic and a production logic to what you do and what you design becomes this sort of larger idea, right? Okay, so anyway, these are what the outcomes will look like. And here's some examples, right, where you start to see, here's the example of a surface that's been broken up into a two-way ribbed grid shell system. Okay? We'll talk about grid shells in a moment. And then on top of that, in each cell, there's a shading component that populates each cell. And each one of these, while they're very similar, they all look like they're brothers and sisters or cousins, right? They all come from the same sort of genotype, right? But each one is slightly different because each cell is slightly different, and each cell's orientation to the sun is different, right? And so we can begin to differentiate each of these cells, right? Each of these components. In order so that the south performs, let's say the south facing cells perform in a certain way, the north facing cells perform in a certain way, etc. Right? And so then you can see how this gets laid out into a set of components that can be unrolled and flattened, right? You can see that there's, a set of edges that can be scored with the laser cutter, so you can actually start to make folds in the chipboard, and then some through cuts so that you start to get all of these shapes, and then labels on each one, right? Same with the rib system, right? You can start to see that we start to get these ribs, and then we start to get these notches, and then we can actually put them together and start to notch them together and then zap them in place with our zip kicker and our Zap-A-Gap glue, etc. Right? So you can see several different ways that students have approached this in the past, but for the most part, it starts with something fat. We turn it into a bunch of pieces that are flat. We laser cut those. We learn a heck of a lot about how to laser cut these things and how to put them together and how to dial in those tolerances. So we start to take into account things like material thickness and the sort of imperfections of a physical material, and sort of negotiating the amount of accuracy we go with the digital model, right? We can sort of take those two things, once those slam into each other and we run it through the prototype feedback loop once or twice, right? You start to get some really interesting results. And I'll show you. I have my office is populated right now with the last grid shell examples that I collected. So I can hold those up and we can talk about them when we get to the laser cutting stuff, and talk about some of the lessons that we can learn from classes past. Okay. So this is the kind of drawings that we'll be producing. And here's a collection of some of the better grid shells that I photographed over the years, from the last 2 years, actually, from some of your peers in the last, I guess, the last 2 years, right? And so sort of putting them together in a grid, you can see, right, just to give you a sense of what these look like, right? These are chipboard. And again, there's a sort of library of different sort of component types and how they're deployed in their cells, right? There's some symmetry or asymmetry. The apertures get larger or smaller, right, depending on how much light they're trying to block. Okay. This is what the schedule looks like. This project will last all the way until mid-November. Okay. Mid-November is where things in your studios really start to hit the fan, I think. You really start to ramp up and get busy. And so, by mid-November, I really want to wrap up this project so it's not in the way of you sort of finishing and trying to get things completed by Thanksgiving and then that week afterwards in your studios. Okay, so we will have a project 3, and it'll be less involved. It'll be stuff that we can do during class time, and it'll actually be really interesting and fun. But it'll be stuff that you don't actually have to work outside of class to do. As long as you come to class every morning, we'll be doing it step by step together in class for that project 3. Those are the last couple of weeks in the semester when you're just at your busiest and your tiredest. Okay, I understand that. It hasn't been that long since I was, I have deadlines, everybody does, right? So, but I do want you to get something useful out of that project 3. At the same time, I don't want to run you too ragged. Third year is a pretty tough year. And so all I ask is that you come to class on time and you can get project 3 done. So anyway, project 2 here. Today we'll talk about project 2 launch, and I'll give you, there's some surface videos that you'll watch between now and Wednesday, so we can have a more intelligent discussion on Wednesday. On Wednesday, we'll talk a little more about planar fabrication, surface to grid shell. I'll actually give you a Rhino script that you can run to actually generate some of this geometry. On Monday, a week from today, we'll actually have a special guest, Kyle Keithis, who runs the Fab Lab here. And he'll be talking and going through the steps about how to set up your files for the laser cutter, how to prepare for laser cutting, how to sign up for laser cutting time, all those sort of how-tos, right? So everything you wanted to know about laser cutting, but was afraid to ask. And then it says Rhino scripted reduction, but I'm actually going to try to give that to you on Wednesday this week, so you can run things on that. So at that point, right, we'll actually start to generate some of this geometry and break the grid shell that you're given the next time we meet. You'll be given it over the weekend into componentry. You can start to format that for laser cutting. You can start to sign up for laser cutting time in the future. But then we'll start to talk about the components that populate each cell, and you'll have some more videos to watch. And we'll start to do some more in-class demonstrations, right? We'll start to talk about performance and how not only when you start to develop your shading components, but then how we can start to measure how well they perform and start to tweak them in order to make them perform better when it comes to blocking certain sun angles and things like that, right? So that'll all be through Grasshopper, Rhino, preparing some things in Rhino and maybe even some Illustrator. I'm not sure. Kyle will tell us what the preferred file types are for the laser cutter at this point. So by Monday, 25th of October, right, you'll all have probably signed up for laser cutting time slots by then, but that's when we'll say, okay, now let's start laser cutting your first prototype. And if some of you are ready to go before then, you can absolutely do it before then, right? So we'll play this by ear, and I'm very flexible in trying to speed things up where we can, right? If I don't want to beat a dead horse if we're going over things and you guys are speeding on ahead. But at the same time, if we need to sort of pause and focus on something a little deeper, we can as well, right? So I've done this enough that I can sort of read the room and give more time where needed and speed things up where needed, I think. It's a little harder in remote, but we can do it. At that point, right, in parallel with you developing your first prototype, which takes time, right? Because you can't all just do it at the same time. So it's sort of staggered over a week and a half or so. But at that time in parallel, we'll start talking about taking that vector information that you're using for the laser cutter and start producing diagrams with it. And to sort of talk about the sort of componentry and how those are laid out, how they're labeled, as well as how they go together and fit back together into some sort of three-dimensional model, right? So, but suffice to say, we'll take a look at the results, then we'll assign the final prototype. And again, you'll be prototyping. You'll also be producing the drawings. We'll have a lot of troubleshooting, debugging to do, right? And oftentimes, a lot of these towards the end will be Q&A and work sessions inside of class time where I can just help you, right? So at a certain point, right around November, right, it won't be me just sort of throwing things at you, but it'll be me sort of listening, you bringing questions and problems or showing me things and getting some feedback and some help, okay? And so really, this is about sort of distributing a bunch of laser cutting time over that sort of, from about mid-October to mid-November, so that you have time to produce a prototype, learn from your mistakes when that first one rarely does the first one turn out the way you want, right? And that's just it is what it is, right? What that begins to suggest is that you learn from that. You start to tweak things, right? And so then the second time for their final prototype, you get things right. I'm going to start calling around to Desert Art Supply and Blix and some other places and start to double check and make sure that they have a supply of 1-ply chipboard. And that's really all you need is 1-ply chipboard, a couple of sheets, right? We'll talk about the laser cutter constraints, but the laser cutter bed size is actually smaller than the sheets that the chipboard comes in. So you buy 1 sheet of chipboard and you can break it down into 2 plus sort of 18 by 32 sheets of chipboard or whatever that fits in a laser cutter by just simply trimming it with a utility knife or an X-Acto knife. So again, we'll talk more about that, but this is not going to be an expensive proposition, but you will have to buy some materials, primarily a couple of sheets of 1-ply chipboard, which isn't too bad, depending on where you get it, $5 to $8 a sheet, I think. And probably some super glue and some zip kicker and maybe some, we'll talk about this, but when I'm putting these together to start off with, you start to put these notched ribs together. As you start to fit more things in, they start to want to come off the other ones that you've already done. And so I get these sort of zip ties and start to zip tie and lock things in temporarily, as I start to sort of interlock things. And that way it sort of has some give to it, but they won't come apart while I'm trying to sort of put things together. So as you move from one end to the next, and we'll talk more about that here in a bit, but again, just be prepared to buy a few supplies. But it's not going to be anything incredibly expensive by any means. All right. Okay. So we'll just go to today, right? And we'll talk about what you need to do between today and Wednesday. And then I'll show some examples in Rhino and Grasshopper of some of the things that you'll be doing off the bat here. So first and foremost, here's some videos to watch between now and Wednesday. These will help you out quite a bit. But it's going to talk about surfaces in general, okay? And it's going to talk about the anatomy of a surface, right? So if you thought about curves and lines as being these sort of streets, let's say in a grid, and again, we were placing points on lines and curves, right? By giving a sort of T address along them, right? So if you think about a street address, let's say Tropicana Avenue, right? So I can locate an exact location on Tropicana Avenue with one street address, right? Like let's say 4505 West Tropicana. I don't know where that is necessarily, but that would be one location, right? Now, if you think about a surface, slightly different. Oh, I guess someone just rang my doorbell at home. But if you think about a surface, it's just slightly different in that if I'm thinking about, let's say, I'm out in, let's say, hiking in Mount Charleston, right, where I'm not along a street or something, or I can't give you a street address, right, like I would, let's say, to deliver something to Amazon. One thing I can do, though, is give a latitude and longitude in order to sort of find a coordinate along this sort of uneven terrain, right? And so that's similar with surfaces, right? We can actually determine a latitude and longitude, right? A sort of a U and a V coordinate along a surface. And so we'll talk about that here in these couple of videos where we start to define a point along a surface. We need two sort of coordinates, right? A U and a V, right? A sort of latitude and a longitude in order to sort of locate an exact discrete point along a surface. All right, and we'll start to break up large surfaces into smaller little checkerboard surfaces, okay? And we'll talk about those latitude and longitude lines. Oftentimes you see those lines already drawn as isoparms, right? So you start to see a surface in Rhino, you start to see that sort of checkerboard running in both directions. Those are called isoparametric curves. And that's what we'll use to start to generate, let's say, surface geometry like ribs going in one direction, ribs going in the other direction, right? That we can then extrude and offset in order to create structure, right, for our grid shells. Here in a moment, I'll talk about grid shells. So we'll talk about surface properties and things that we can do with surfaces. You'll actually build a surface from a set of points that actually moves. And then, just as a fun thing between now and then, we'll actually deploy a bunch of trusses along a surface. And that just sort of brings your truss assignment all the way around full circle to here's how I would actually do it, right? If we were thinking about how to do this a little easier now. Anyway, we're going to move on from that the next time we meet on Wednesday. We'll start talking about grid shells. So, grid shells. And I'm going to pull up probably a really quite famous example that you can see, right, what we're talking about here with grid shells, right? Oh yeah, look at that, right? That's exactly what we'll be doing, except with chipboard, right? So you see these sort of notched assemblies, right, where the sort of structural members are curved, right, in order to sort of form a grid shell. There's a really famous one by a German architect / engineer named Friado. It's this gorgeous one that he did in Germany, right? And so oftentimes what you'll find is that grid shells and shell structure geometry in general are an interesting sort of a thing, right? You can start to model, I think, much more complicated dome-like or doubly curved surfaces with them. And they perform in really interesting ways, right? There's a sort of structural redundancy, right? So for instance, what I mean by that is if I took out exactly one of these ribs, there's a redundancy to this. The whole thing wouldn't just crash and burn and explode, right? It wouldn't just fail. right? But there's a redundancy to this that you could actually begin to remove one or two structural members here, and the system could actually still redistribute loads, structural loads, across the system in multiple directions, right? And that's the key, right? Unlike a grid, like a post and beam system where we have beams, linear beams that go then distribute the load halfway to columns and then down to the ground. And if we remove some of that stuff, everything's been sort of optimized so that if we remove one member, things really will fall down and fail in terrible ways. With these, we have this sort of loads are distributed in multiple directions, right? And so, you can begin to see that because of all the nodes, right? And all of the struts in between, again, the loads can do some pretty interesting things, and we can do lots of interesting things with geometry, right? So anyway, I just wanted to sort of bring that to your attention. There's lots of different ways we can deploy shells and grid shells, but this is a super famous one, the Mannheim multi-hall, right? By Friato. Just sort of really large, elaborate gathering space that was actually quite simple in structurally, right? Okay. So now I'm just going to do a few quick demonstrations. One of the things that you'll be given the next time we meet on Wednesday. Oh, now what? Come on, Windows. It's like I've had this up for how long? All right. Is you'll be given two different surfaces. Okay, one is doubly curved. And you can see the isoparms, right? Let's say these are the U direction, and then these are the V direction, right? Latitude and longitude lines that go across this, right? There's an equator and a prime meridian, right? Going in opposite directions. And what the result is a checkerboard running across your surface, right? But one example, one of these surfaces, right? The concavity and convexity is in both directions are going in the same direction, right? And so what we end up with is a dome-like shape. In the other one, you can see now highlighted magenta, right? Concave in the U is pointed up, and concave in the V is pointed down, right? So we get a saddle shape. They're still both of them are doubly curved, right? But we get a sort of different surface classification, right? Here we get a saddle shape, right? Where we have U's moving in one direction and then the other direction, right? These sort of parabolas that are formed. Here, the parabolas, the sort of apex of the parabola, right, are running the same direction. They're both at the top. Okay, so you'll be able to pick from one of these, right, to sort of do this assignment, project 2. So I'm just going to show you some of the things, just as a sort of sneak peek of some of the things that we'll be doing here. All right. Oh, let's see here. I don't want that one. All right, so a couple of things in Grasshopper, we'll be taking some of these surfaces, breaking them up into smaller quad-like components, and then unrolling them as strips, right, that can actually be flattened out. You can see that these are all like sort of overlaid on top of each other. I need to sort of spread these out. And at the same time, once we develop these sort of cells, we'll actually be placing three-dimensional shading geometry on them, right? So here's my example. It's like half of a four-sided pyramid. Then we'll actually be laying and flattening these things out and unrolling them onto the XY plane, spreading them out, giving them all a sort of label. You can see that they all sort of change, right? And preparing them for laser cutting. So you can begin to see, in this case, I'd go through and score this edge for each one with the laser cutter, so it only cuts part of the way through the material, right? So we can actually do that with power and speed settings in the laser cutter and just score. So that way we have a nice perfect fold, right? And then I'll go back through and then do a through cut to cut all these custom shapes out, right? And at the same time, you'll score in a label here so that we can begin to understand which one is which. Otherwise, it's too big of a geometric jigsaw puzzle for you. So we'll be learning how to do all this stuff. Let's see, let me cancel. I think I have another one open here, performance feedback loop. The other thing is we'll take these components and then we'll be able to I'll actually give you a few different sun rays, right? And then you'll actually measure how much solar radiation that your surface receives. And then based off of that data, you'll begin to actually plug that data in and begin to change the surface geometry. And so you can see that this is the exact same shading components, but now you can see, okay, the blue areas that are mapped on the surface have a lot less direct solar radiation. And so the shading components are a lot smaller. They don't need to actually close up the cell and block any direct sun. The parts over here that are shaded in red and orange, on the other hand, actually have quite a large amount of, the shading components actually get a lot larger and they cover more of the cell, each cell, right? In order to sort of, again, provide shade where you need it, right? And so what's interesting about this is you can start to use the parametric model, take the performance constraints and actually use it to generate this sort of differentiation that occurs over the course of this grid to create a sort of gradient, not just in coloration, but in the geometry itself, so that the parts where you need larger closed off, larger shading components that close off the cells in order to create shade can, and the ones that don't are much smaller and actually allow views in and out. Okay, so very similar to that example I showed at the very beginning from Adelaide, Australia. All right. Maybe we'll look at that again on Wednesday. Right, and so what we're doing is we're taking some sun rays, we're measuring performance, but then we're mapping the data as color. So we get a visualization across the surface, but we're also using that data and then beginning to feed it in, right, to the geometric recipe, the algorithm that produces these components, right? So you can see that it begins to directly inform, right, the sort of this data right in here, and begins to directly inform the geometry of each shading component. And then of course after that we can take each component and lay it again out for laser cutting, right? So one last thing I'll show you here, and this is the first steps for how we're going to generate the structure, right? That sort of two-way rib system that these components that you laser cut will sit on top of, right? So the grid shell itself, right? And then there's the shading components. I'll just run a Rhino script. Again, we'll talk about this on Wednesday and I'll show this in detail, but I'm just going to give you a taste. Just say, I'll bring up the script editor here in Rhino. So what I'll do is I'll give you a Visual Basic script that you can run. And let me see if I can find. Here we go. All right. There we are. So what I'm going to do is I'm going to run this and you'll see what it does. I'm going to go to the command line. It says select a surface to populate with tiles. I'm going to select that surface. And it says enter the number of tiles in the U direction. I'll say 20. And then the number of tiles in the V direction. In other words, the number of cells in both directions. So in order to make a grid. And then enter the height of the strip. This is the depth of your sort of your ribs, your structural ribs, your grid shell. I'm going to say 0.25, let's say 1/4 of an inch or something. And then the X distance between unrolled strips, this is how it lays them out. I'm just going to give, I'm not sure what I need for this, so I'll just guess. I'll say 10 inches and 20 inches. And then the material thickness. We'll talk about this in a bit when I measure some 1-ply chipboard, but I'm just going to say 0.03. Let's just say it's a 32nd of an inch, right? So that would be 0.03125 or something like that, 0.0625, 0.03125, or I can't remember offhand, but I'm just going to say 0.030, and let's see what it does. Now you're going to watch, it's going to go through here, and you can see the command line is scrolling through. I've turned the redraw off because it goes quicker if it doesn't have to redraw things in real time. Once it's done computing all this stuff, it lays all this stuff out for me, right? And so you can see as I close this, don't save. And I'll just hide this original surface. It's converted this surface into a set of ribs, right? And if I select each of these three-dimensional ribs, I go to the properties, it's labeled each one. So this, for instance, this is the 10th one in the U direction, U10, right? If I go to the next one, that's U9, U all the way to U0, U0 all the way to U19 probably, right? Because I did 20, maybe 20 divisions. So yeah, U20, right? All right. I'm not sure why this is, I'll fix this weird output curves layer thing here and make sure the labels are working for you. I have a sneaky suspicion that there's a couple of Rhino methods that have changed between Rhino 4 when this was developed and Rhino 7. So I'll just need to fix a few things in some of the sub-functions at the end. But it also lays all of these ribs out for you for laser manufacturing. And in fact, it lays out these score lines to help these things sort of bend a little longer. Then it also gives you the notches. And these are things that can just be cut out, right? And then cut the overall shape out. And so that gives you the U's and the V's. And honestly, there's something I really quickly have to fix here. It'll also give you the labels and actually give you the sort of typeface labels here. But honestly, what I'm going to do is I'm going to tell you to create those labels again yourself using a single stroke font in Rhino. So we'll talk about that stuff later. But this will speed things up considerably, right? Because now I've gone from something three-dimensional to something flat, right? Very quickly. And from here, it's just a matter of keeping things organized and then pushing these things all together, right? And getting them sort of quickly, let's see here. Keeping these things, but moving them around so that I sort of nest them really closely together so I can maximize the yield of material that I get from the laser cutter. It's really important. You try not to you try to minimize the waste, right? And you get these funky shapes in a rectangular sheet of chipboard. That's really the key, is how do you start to push these together and make sure that you don't waste too much with all the sort of scrap offcuts, things like that, right? So again, we'll talk about all this stuff, but this is the key, right? Leveraging computation to do some of this hard work for us, right? And then, here's the thing, right? When I can generate this in 20 seconds, I can generate lots of different options and sort of evaluate, okay, what thickness do I want, right? Is this too thick? Is this too thin, right? Maybe I also play around with the spacing, right? Maybe 20 by 20, what does that give me? That gives me 400 cells. That means 400 components. Maybe that's too many. Maybe I dial it back and say, okay, let's see what it looks like when I do 10 by 10, right? That gives me 100. So then I basically cut the amount of components by, all the way to 25% of what was there before, right? So trying to find that sweet spot, right, between the complexity that you want and the aesthetic that you want, right? But also looking at the amount of components and the size of them relative to the thickness of the material, right, are things that you can dial in and quickly rerun this, right? So this is scripting is basically Grasshopper, but you have to write code, right? You have to sort of write it all out. Grasshopper is scripting, but visually, right? So it's much easier for us. But I've already given you, I'll actually give you the script that you can then open up in the editor and then run and execute and re-execute. So you can begin to look at this over the weekend. All right. So again, that's just a sneak peek of what's coming up. I do hope you get excited about this, because this is where, we really start to produce something that could become architecture. I've always wanted to sort of, take this as some sort of industry partner here in town and sort of say, hey, what would be really cool is, if you sponsored us so that we could actually build this at full scale and make a pavilion out on campus somewhere, like this grid shell pavilion. But I haven't figured out how to work that into a semester with 40 or 50 people in the class yet. So, but honestly, this material can scale up, and we'll talk about that when we talk about the sort of planar fabrication, digital fabrication side of things, right? We have laser cutters that cut at a particular scale and thickness of certain materials, but we have high-powered laser cutters that can cut things out of steel and aluminum. And we have other sorts of machines that are similar in logic that can cut things out planar, right? We have out of using CNC technology, just like a laser cutter. We have routers that do similar things, right? In fact, we have a larger router, CNC router in our shops here at school that can do this. But out of like plywood and maybe even non-ferrous metals, really soft aluminum alloys. If we're there spritzing it with, to cool off the tool, so it doesn't get too hot. We also, or plastics and acrylics and things like that. We also have a CNC plasma cutter, right? That's sort of taking a torch that can cut through things like sheet steel and even, I guess, thinner plate metals if you really want to, but that could be ferrous metals as well as non-ferrous metals, right? So this stuff does scale up. There are also water jet cutters that can cut through incredibly hard things, right? Water jet cutters can cut through stone and titanium and all kinds of really thick and tough materials. But anyway, so these things can scale up and to more larger and or full-sized architectural components. So this is good practice because honestly, I mean, I've taken DXF files, or Rhino files, that I've done with laser cutting and taken them and had them cut out with, by actual laser, larger laser cutters or plasma cutters, right? So in fact, there's furniture here in the building, right? Paul, who runs the wood shop, and we've basically scored and cut through steel, score the steel, right, with kerfs so that you can actually fold it by hand in order to make legs and other sorts of three-dimensional things out of flat pieces, right? So you can even turn steel into some sort of origami full size. It's really quite an interesting thing. And I have prototypes sitting in my office actually when we were first starting that process. So again, I hope this sort of opens your eyes up to larger things. You don't know what you haven't seen yet. And so I hope that this class also introduces you to projects out there. If you've looked at any really good and interesting contemporary architecture the last 20 years, you maybe begin to understand that you need to learn these tools because honestly, the days of just sort of making a bunch of paper drawings from AutoCAD are gone, right? And so, dealing with geometry, dealing with parametric design, later on with BIM, right? Rhino, Revit, and all of those sort of tools to generate the visualizations with Illustrator and Photoshop. I mean, those are the tools that we primarily work with on a day-to-day basis here. So again, this is meant to be a crash course, but I hope you can sort of begin to integrate these tools into your other design work as you go, right? All right, so that's a lot of talking on my end, but we have about 20 minutes of class left. We're done for the day. Again, just as a quick reminder, while I'm sharing my screen, right? You need to watch these 4 videos between now and Wednesday. Try to follow along a little bit if you want. It's not necessarily mandatory, but I want you to sort of watch and look and see what's happening in these, right? If you actually build anything and play around with these first 2, right? They're a lot easier and more accessible to do. This one's just a fun sort of thing to sort of show you some more how we build off of points, lines, curves, and then surfaces. And then again, to sort of take the trusses that are still burned into your brain, how we would implement a set of trusses or truss system along a surface. But these 2 things are really important. On Wednesday, I'll give you some files that you can start to explore. On Wednesday, you'll have a different type of video to watch over the weekend as well. And then a week from today, we'll start talking about planar fabrication with Kyle with laser cutting. Okay. For the next 20 minutes, I'm still here. If any of you are having any major issues with trying to submit project 1, now would be the perfect time to let me know, and I can help with any very last second, 11th hour problems that you might be having. But the rest of you are dismissed. I look forward to seeing you on Wednesday. Okay.
Thank you.
Yeah. I'm gonna stop sharing now. Stop recording.